Good day, Cecil College students. Lesson 9, video C. A couple of examples to talk about slope, talk about the y-intercept. This might be my shortest video ever. Let's see if I can try to keep it under 8.5 minutes, but who knows. Example, for each scenario, we're going to interpret the slope and interpret the y-intercept in the context of the problem. So we'll understand what the problem is talking about. Excuse me. Interpret that slope in the context. So, part A. College instructor created a linear equation to predict the y variable is student's final grade, the number grade, so 92%, 87%, 52%, based on how many absences. So the x variable will be how many classes you were absent for the semester, and based on your absences, we'll try to predict final grade. 58 students in the class. Here's the equation. We'll pop a hat, put the hat on in your notes here for students' final grade. We're predicting y. The software that we use to make these has a hard time putting hats on the words, so we'll keep putting them on in the notes. Students' final grade is predicted to be 96.77 minus 5.19 times number of absences. Be careful, students. This is the slope. Slope is always the number connected to the x variable. That's your x variable. Remember down here, this will be the y variable, and the number all by itself is the value of the y-intercept. Interpret the slope in context. What the heck does this mean, this negative? Careful, it's a negative. Negative 5.19. All right, so we'll just say it first, then we'll write it down. The model is predicting that for each class a student misses, for each extra absence, the grade is predicted to decrease by 5.19 points. That's what the model is telling us. Of course it's not true. If a randomly selected student missed a class, would we expect their final grade to go down by over 5%? Probably wouldn't happen. They could lose more, could lose less, no change, but that's what the model is telling us, and the model is based on the data that we collected. All right, here we go. We'll write it down. For each additional class missed, the model is telling us grade decreases by 5.19 points. I'll even write that. The model predicts grade to decrease by 5.19 points. In general, as x increases by 1, x is number of absences. For each extra absence, grade is expected to decline or decrease by 5.19 points. Okay. Let's interpret the y-intercept. We know what the number is. It's right here, 96.77. A couple of things need to happen for that number to be meaningful. Number one, do I have any data near x equals 0? X is number of absences. Do you think out of 58 students, we might have some 0 absent students? Most surely, right? So we do have data by x equals 0. Does this value make sense? Could you imagine a student getting a grade of 96.77? Surely. Both conditions are met. We have data near x equals 0. This number is reasonable. So what the heck does that mean? A student with, I'll even put x equals 0 absences is expected to earn a grade of, let's emphasize this is y equals 96.77. A student with x equals 0 absences is expected to earn a grade of y equals 96.77. The data is telling us these facts. These are our best guesses for all students who might take this course. But remember, this equation is based on the data that the instructor collected. All right, A is done. We'll move on to B. And here comes B. A geologist collected data from 77 elevations up in the Rocky Mountains during last December. Elevations were listed in thousands of feet above sea level, and those elevations were used to predict temperature. As we probably know, the further you go up in elevation, up in the mountains, the colder it typically gets. I see this a negative slope again. That's telling me yes, as elevation increases, temperature tends to decrease. We'll put a hat on temperature. We're predicting temperature. Again, this is our y value. X is over here. Elevation, the slope, is the minus 5.6. And again, this is the y-intercept. Interpret the slope in context. Interpret the y-intercept in context. Okay, let's do it. Slope. As I go up by 1, as elevation increases by 1. In this case, I read the problem that's elevation in thousands of feet. So for every 1,000 feet, we go up. For each 1,000 feet up in elevation, we expect temperature to decrease because the slope is negative. By 5.6 degrees. Does it say? It does say Fahrenheit. Always want to put the units, so feet and degrees Fahrenheit, period. For each additional, or for each 1,000 feet we go up in elevation, we expect to decrease by 5.6. You'd probably throw the word temperature. We expect temperature to decrease by 5.6 degrees Fahrenheit. Here's a little hint, and do this. Read what you've written before you turn it in. We're interpreting these numbers. They need to make sense for others to read them. So I see we need the word temperature so that it sounds good, it makes sense. Okay, so that's the slope. Let's talk about y-intercept. Y-intercept is 60 degrees Fahrenheit. I look at the problem description. It says data was collected up in the Rocky Mountains in Montana. Elevation of 0, x equals 0 really doesn't make sense for this data set. We sort of have to think outside of the box here. X equals 0 feet above sea level. Well, that is sea level. And this problem is about data collected up in the mountains in Montana. That's not in our data set. It just can't be. I mean, we don't need to be geologists to really make a common sense evaluation. X equals 0 feet above sea level is not in this data set. Exclamation mark. It just can't be. If you understand the problem, you know that we're up in the mountains. So that means that the y-intercept is really not interpretable. It's just a point on the graph. If I graph the equation, this point and that point would be 0, 60. This is x equals 0 for the y-intercept. This is the y-intercept value is just a point on the line. That value of 0, 60 on the graph, we really shouldn't interpret it. We really shouldn't predict that, oh, up in Montana in December, if I'm at sea level, I would predict the temperature to be 60 degrees. It's probably a lot colder up in Montana than 60 degrees in December. All right, so we got a little practice interpreting slope and y-intercept. Now that we can do that, I think the next step is to actually come up with equations to solve for these values. So we'll let Kim take care of that in the next video. Thanks for watching.